Okay, welcome to 8.3, lecture number 3. If you will recall, we left off figuring out how you can figure out the percent ionization, which is just, basically how much of it ionizes. You can see for this example that we did a very weak acid, a very, very small percentage of ionization. So what we're going to do now is do a little different twist on these same problems. If you remember the previous two problems, we could find Ka because pKa was given to us, and I don't see any pKa here. However, I do see a percent of ionization. All right, so looks like this one ionizes quite more readily, not enough certainly to be a strong acid, but this is acetic acid making the hydrogen ion and acetate. So how do we go about doing this problem? Well, we can't find Ka like we did the other way. So we'll just skip right to the icebox. That was step 2 in the other problem. And that part will be pretty straightforward. You got the 0.3, 0, and 0, the minus x plus s plus x plus x, and the equilibrium, and hopefully you're really comfortable with that. Well, here's the thing. If you know the percent of ionization, you can figure out the concentration of this negative ion. Remember we said you take that over the original acid will give you that percent. So we can figure out the C2H3O2, the acetate ion, by just doing this. Taking the original concentration and multiplying it by, and this is important, remember it's a percent, so you have to move that decimal point 2 places. So you can see that this is the molar concentration, so that would equal this, which of course would also equal the hydrogen ion concentration. So you can work the problem backwards. Not too difficult of a concept, really. You have that initial molarity, and you know what percent it ionizes in the solution, so you just multiply those out and end up with that percent, which of course you can now plug into your Ka formula. There's the hydrogen in the acetate over the acetic acid. We just figured this out. That's 2.30, and of course these two will be equal, so that's why it's squared. And then you take 0.30 minus 2.3, and you can actually just plug these numbers into your calculator. If there's no x, you don't have to go, oh, do I need to include that one or not? It'd be interesting to see if it changed your answer if you want to try that without, but I would err on the safe side and just plug the numbers in your calculator. Just use your little parenthesis keys there, and then you find out that Ka equals 1.78 times 10 to the minus 7th, kind of a middle of the road Ka value for these weak acids that they're going to be about. Not super weak, but it's not hydrofluoric acid either. So, but it's getting close to that, a little on the stronger side. So to find the pH, you've already got the hydrogen ion concentration, so you can just do the negative log of that. And this is one to be careful with. We recognize that we are at 3 sig figs, so 2.640 is the pH in that particular problem. So you're kind of working the problem backwards to give the Ka and then the pH eventually. Okay, so that's kind of just a little different twist on those same problems. Okay, so let's see what we got coming up next here. Defining weak bases will react with water to form those hydroxide ions. The equilibrium, as you would think, normally lies really far to the left because they're weak. So you got a lot of it just wants to kind of stay this way and not drive the forward reaction. So now this says find the pH of a 3.5 molar NH3 solution given this pKb value. And I think you should be able to certainly get started with this. So we're going to work this through as a KB problem instead, but the concepts are the same. Raise that to the negative power, this has 2 sig figs, that has 2 sig figs. So your KB value also at 1.8 times 10 to the minus 5th. All right, so you're going to have to do an ice box on this one as well. You might want to hit the pause and make sure that you've got this down, but I'm assuming that this is really just something that should come out real smoothly for you at this point. Okay, so this is going to allow us to solve for x in this equation. This one kind of skipped ahead to go right to the math, which is your 2 reactants over your product in this case. We can make this assumption that it's 0. All it has to be is the definition we used at one point was smaller than 0.0001 or 4 places to the right. You saw one of the examples we did last time. It was really close to changing the value, but that's not going to affect your 3.5 at all. So you take the square root of the KB, which we already figured out was 1.8 times 10 to the minus 5th, times 3.5, and you end up with 7.9 times 10 to the 3rd molar. All right, so now that's the hydroxide ion concentration, of which you can do the pOH, negative log. It's going to be about 3-ish, somewhere in that zone. Make sure that you're punching all these in and getting the right answer, but when you solve for the pOH of this solution, that's 2.10. But if we zip back to the beginning, it says find the pH of the solution. So to do that, you need to, again, if you want to, use those purple sheets, and you see that pOH plus pH equals 14, that equation is right there on your purple sheet, the 3rd from the bottom in the equilibrium box there. So you just realize that the pH is 11.90, and then most of us are a little more comfortable knowing that the pH is basic if it's above 7. Okay? And that's usually a question they'll throw at you. Is it acidic or basic? All right? So here's another problem where you start off with a known pH, and it's a 0.15 molar ammonia solution, and then it asks you to find the pOH. Well, the way you're going to approach that, again, if you know the pH and you want to find the OH, you got to use that magic number 14, subtract the 8.75, and again, don't get hung up on 14 having 2 sig figs. This guy's 2 places to the right, so your pOH also will be 2 places to the right. Now, if you want to find the concentration of OH given the pH, you use this old trick right here, that both of these things will equal each other, but you raise the 10 to the negative POH. And crunch those numbers. That's 2 sig figs, 2 places to the right. You'll need 2 in your final answer. So 5.6 times 10 to the minus 6 molar. Just kind of working these problems from all angle, and that's why spending some time on these practice problems is going to be real good. Okay, now what about KB? So we got the OH concentration. How are we going to move that into finding a KB? Well, if we know the concentrations of everything, and we do, then you can just plug them into your equilibrium law expression. These are equal. We worked hard now to figure out what the OH was, and it would be the same as the NH4, and then you divide it by the original 0.15, which is unscathed mathematically by these small amounts. So KB equals 2.1 times 10 to the minus 10th, and that's just crunching these numbers here. And that's how you figure out a KB. And then the last section that we're going to get here is polyprotic acids. So you have something like H2SO4. So we call it polyprotic. Self-defining term means many protons. Many protons. In other words, more than one proton. So sulfuric acid, good example. Carbonic acid, phosphoric acid, H3PO4. You could see those guys. Anytime they have more than one hydrogen, then you could have this happening. Okay? And we talked about this a little bit, that you deal with one hydrogen at a time coming off. So H2CO3 becomes HCO3 minus. Because remember, you're taking the hydrogen and it has a positive charge with it. Okay? So you're leaving the electron that it had involved with the bond. The electron's still stuck with this guy, so it's a negative charge. And you see the charges, plus and minus, balance each other out. And then we call this Ka1. And you will notice that it is a higher number than the Ka2. That's always going to be the case, because this guy is a little bit less likely to rip off of there for lots of reasons. It's got the negative charge on there, kind of holding it intact. Just much harder to entice that second hydrogen off there. So that means if you're going to do some calculations and you're given these various Ka values, there's one little trick to remember here, and that is use Ka1. All right? Why? Because it's a bigger number, and even if it was close, if you think about it, that first hydrogen comes out is adding hydrogens to this second reaction, which will shift the equilibrium to the left, making even fewer hydrogens and making this number even smaller than it already is. So this really becomes a non-factor. But knowing that is important. They'll give you a whole list of all these Ka1, Ka2, Ka3. Just use the Ka1 to calculate the hydrogen, because it's greater than the Ka2 by a considerable amount. And again, this explains that it'll also drive that equilibrium farther to the left. So you are now certified to do all of the 8.3 problems. Answer key is posted. So good luck with those, and they'll do pretty much the same types of things. It's just good to hardwire this acid-base equilibria. So this is the last lecture for 8.3.